Okay, in this problem we need to graph the rational expression x squared minus 9 over the quantity x squared minus 1. Now remember, we get information about our graph from both this expression for y as well as the expressions for the derivative and second derivative of y. So it will be important to go ahead and crank these two guys out first before we do anything else. Starting with the first derivative of y, we notice of course that y itself is a quotient, and so to find the derivative we'll need the quotient rule. So it looks like we need to start with the denominator, or the bottom guy here, times the derivative of the top. Of course the derivative of the top is just 2x, minus the top guy, or numerator, times the derivative of the bottom guy, which again is 2x. All of that over the denominator squared, like so. This of course can be cleaned up, it can be simplified. First, notice we have a common 2x on both of these terms here in the numerator, so let's pull that out. So we get something like this. And by the way, this is a good habit to get into. After an application of the quotient rule, you should check to see if you have any common factors in the terms of the numerator that can be pulled out. This frequently makes the simplification much, much easier. Of course, then we have an x squared minus an x squared, so those are going to cancel. And you also have a negative 1 minus a negative 9, which is a positive 8. So combining the 8 here with the 2x, we have 16x over x squared minus 1, that quantity squared. Now this is pretty tight, this is fairly simplified, so let's turn our attention for the moment to the second derivative. Again, we're taking the derivative of this, which is a quotient, so we use the quotient rule again. So we start off with the bottom guy, the denominator, times the derivative of this numerator, the top guy, so times 16, minus the top guy, 16x, times the derivative of the bottom guy. Of course, this requires a chain rule application since this is a composition. We've got a polynomial inside a squaring function. So we bring the 2 down from the squaring function. What's left is raised to the first power, which I don't need to write. Of course, the inside piece remains the same here, as long as I remember to, by the chain rule, multiply by the derivative of what's inside. So of course I'm multiplying here by 2x. So that's the bottom guy times the derivative of the top guy, minus the top guy times the derivative of the bottom guy. All of this must be over the bottom guy squared, or equivalently x squared minus 1, that quantity to the fourth. Here again, I want to tighten this up as best I can. Just like we did up here, look to the numerator. Are there any common factors that we can pull off here? Certainly we have a common 16 on both terms, but we also have a common x squared minus 1 that we can pull off as well. So let's put that down and see what it leaves. Of course, to get this term here, we need a 16, we need an x squared minus 1, and it looks like we need a second one. So let's go ahead and put that in. And then to generate this term here, well, we've got this, we've got the 16, but we're missing both 2's and both x's, so it looks like I need a minus 4x squared there to finish it off. Notice, and this happens a lot of times here when we're dealing with derivatives of rational expressions, we have an x squared minus 1 and an x squared minus 1 to some higher power. We can cancel one of these guys off. So that drops the denominator down to the third power. And what's left inside here is fairly easy to tighten up. We have an x squared minus 4x squared, that's a negative 3x squared, which we write here. And then of course we have a minus 1 that we need to throw in there as well. Now this is pretty tight. You might be bothered a little bit by the presence of the 2 negatives there, but that's easily dealt with. We could pull that negative out, leaving both of these positive if we wanted to. There. Now all 3 of these guys, y and y prime and y double prime, are in simplified form. But keep in mind that the interesting features of the graph of this guy are associated often with where these three expressions are either 0 or undefined. Okay, and to that end, an expression like this one is going to be 0 when the numerator is 0 and the denominator is not. So we will want to know what x values make a 0 show up in the numerator. To that end, having the numerator in a factored form might be helpful. The same can be said if we're interested in where this expression is undefined. It would be undefined certainly if the bottom, if the denominator was 0. So being able to find what x values produce a 0 in the denominator will be helpful, and to that same end, factoring the denominator might be useful. Okay, we want to do that for all three of these things because, again, knowing where each one is 0 or undefined helps us find an interesting graphical feature of this graph. So to start, let's look at this guy. Of course, x squared minus 9 is just a difference of squares, as is x squared minus 1. So let's factor both. Okay, so we have a nice factored form for the original function. Moving down here, notice the x squared minus 1 shows up again. That's again a difference of squares. So just making sure this is completely factored, there's not much we can do with the numerator. We would have both of the factors seen up here, just individually squared, since that whole thing was squared there. And finally, turning our attention to the second derivative, we can pull a similar stunt in the denominator to get this. The numerator, however, doesn't factor nicely any more than it already is. I suppose we could force the issue in some cases where the quadratic scene has some real solutions, even if they're not pretty solutions, but here we can't even do that. Look, we're only interested in where this numerator is equal to 0. Factoring is just a vehicle to that end. But look at this factor right here. You're taking a square which must be positive. You're multiplying it by 3. That's going to keep it positive. You're adding some positive number to 1. That's going to put you above 1, right? This factor here must be 1 or greater. Okay? Times 16, negative 16, puts you less than or equal to negative 16. This expression can never be 0. And we would see that very quickly if we just set this whole guy equal to 0 and tried to solve for x. We get a square root of a negative or something similar. Okay, so I'm just going to leave this alone on the top. Okay, so now we have y and y prime and y double prime expressed in fairly tight forms, but where it's still easy to determine where the numerator is 0 and where the denominator is 0, where the overall fraction is 0 and where the overall fraction is undefined. Okay, so I'm going to remove some of this extra work because we're going to need the space over here. Okay, so we've consolidated our work a little bit from what we had before. Notice I left the original expression for our function here, as it will eventually help us out a little bit when we need to consider if our graph has any horizontal asymptotes, but that's a bit down the line. Okay, right now, let's, for each one of these guys, y, y prime, and y double prime, let's draw a line like so. And this is really just to organize our thoughts here. But let's consider where each one of these expressions is 0 or undefined, and then ultimately where each one of these expressions is either positive or negative. Knowing where these four things happen tells us a great deal graphically. Now, we get different information depending on whether we're looking at y or y prime or y double prime, but again, knowing where things are 0 or undefined and positive or negative will really help us flesh out this graph. So let's take the first one. Okay, where is this guy 0? Well, of course, that would be when the numerator is 0, and of course the bottom is not. So it looks like x equals negative 3 and x equals positive 3 are the two places where that happens. So let's mark that on our line here that corresponds to y. Like so. Now, graphically, what's going on here? If the entire expression is 0, notice that means y is 0, which means the height of our function is 0, which means we must be sitting right on the x-axis. So these two guys must correspond to x-intercepts. So let's indicate that like so. Okay? Now, where is this overall expression undefined? Well, it would certainly be undefined when the denominator is 0, and it's very easy to tell where that happens since it's in factored form. This factor tells us when x equals -1 we have a problem, and this one tells us when x equals 1 we have a problem. So let's mark both of those. Okay, like that. Now, what does this tell us graphically? Well, think about the limiting behavior of this whole expression when you get very close to either one of these. Let's say we get close to 1. Okay, so when x is getting very close to 1, this of course is getting very close to 4. This is getting very close to -2. This is getting very close to 2. And this is getting very, very small. And depending on whether we're just to the right of 1 or just left of 1, it might be a small positive value or a small negative value, but it is definitely small. And getting smaller the closer we get to 1. So it's not too hard to tell. Looking at the top, you're getting very close to -8. On the bottom, of course, something that's small when doubled is still fairly small. It looks like this whole thing is getting very, very large, flying off to infinity. Now, it may be positive infinity, it may be negative infinity, depending on what sign this is, depending on what side of 1 you're at. But in either case, we have created a vertical asymptote. So let's indicate that here. Okay? Of course, near x equals -1, the story is very, very similar to this one. So we have a vertical asymptote there as well. Okay, so now we've fully addressed where this guy is 0 or undefined and graphically interpreted the results. What about the first derivative now? Where is it 0 and where is it undefined? Well, it would be 0 again where the numerator is equal to 0 and the bottom's not. So 16x being 0 implies x itself is 0. So let's mark that over here. Now graphically, what's going on at x equals 0? Well, we said the entire expression was 0 there. So the derivative is 0 there. So the slope of the tangent line is 0 there. But a 0 slope is a horizontal slope, so we must have a horizontal tangent here at x equals 0. So we indicate that appropriately. That's when this expression is 0. What about when it's undefined? So again, it's undefined when the denominator is 0, and that again is when x is -1 or +1. It's the same two factors that caused problems before. Of course, here they're just squared. So I mark them on my line. But realize this should not have been a surprise at all. Look, at 1 and -1, you've got a vertical asymptote here. You have a domain issue here. When you have a domain issue, you don't have a continuity. When you don't have a continuity, when you have a discontinuity at -1 and 1, you cannot possibly have a value for the derivative. Okay, so it was bound to show up that -1 and 1 were still problems here, even without looking at this algebraic expression. Okay, so I don't have to put a graphical interpretation on -1 and 1 in terms of the derivative because it's already been covered. We know why it failed. They were vertical asymptotes. Okay, so now let's turn our attention to the second derivative. Here again, where is this 0? Where is it undefined? What about the numerator? Where is it 0? Well, we've already kind of argued through this point. Notice this factor right here is always bigger than or equal to 1. It can never be 0. This can never be 0. So the product of them can never be 0. If you had missed that somehow, you could of course try to solve for where the numerator equals 0 to get something like this. Got all the work here. And notice when you're done, you end up with the square root of a negative number. This is not a real value. It's not in the set of real numbers. Okay? So this numerator is not going to add any ticks to this line. Okay? The second derivative is never 0. However, it could be undefined, and in fact we expect it to be undefined. Looking at the denominator, when is that 0? Again, -1 and 1. Same two problem points we had before. So we mark both on our line. Again, there's no need to graphically interpret either one of these because we know why the second derivative failed to exist. We had a vertical asymptote at each of these x values. Okay, so now we've gone through and answered the question, when are these guys 0 and when are these guys undefined? And graphically interpreted the results as needed. Now the question is, when are these guys positive and when are these guys negative? There are some graphical interpretations we can make in those cases as well. Now, if we've done everything correctly, it should be the case that the sign, positive or negative, can only change at these values of x that I've laid on these various axes. Let's see why that works. Consider the original function, okay? And let's consider this interval to the right of 3. Okay, so I'm considering x values that are bigger than 3. I can figure out the sign, positive or negative, of this whole expression by knowing the signs of each individual factor. If I'm bigger than 3, this is certainly a positive. This is certainly a positive. This is certainly a positive. And so is this. So the product slash quotient of 4 positives, that must be positive. So anywhere here to the right of 3, my original function is positive. And that has a graphical interpretation. If y is positive, the height of your graph is positive, you must be above the x-axis. So we can indicate that accordingly on the line. Okay. Now what if we're between 1 and 3? Say 2, for instance. Well, that plus 3, 2 plus 3, that's a positive. 2 minus 3, or anything in between these two values, minus 3, would be a negative. 2 plus 1, or anything in that interval, would be positive. And 2 minus 1, also positive. So it looks like we have the product slash quotient of 3 positives and a single negative. So that must itself then be negative. Graphically, of course, if y is negative, the height of your function is negative, you must be below the x-axis, so we can graphically interpret it in that way. Okay, so we write that down. On the other side of 1, and between -1 and 1, let's say 0 is a nice representative example, we can see this factor is still going to be positive, this factor is going to be negative, this is going to be positive, this is going to be negative. Looks like we have 2 negatives that will cancel out. So this whole thing should be positive, and we should again be above the x-axis. Between -1 and -3. See, -2 is a nice representative value we can plug in here, but this works for any value between -1 and -3. This would be positive. -2 minus 3, of course, is negative. -2 plus 1 is a negative, and -2 minus 1 is also a negative. We have 3 negatives and a single positive. The overall product slash quotient must be negative. And so we're again below the x-axis. And finally, if x is left of -3, maybe we plug in -1 billion or something, it's fairly clear that all 4 of these factors are negative. They all cancel each other out, and so we're left with something positive, and we know our function is above the x-axis. We can do a similar analysis down here for y prime. To the right of 1, well, let's see, what do we have? We've got a 16 times an x, which is a positive, over a whatever this is. Maybe the x plus 1 is positive, maybe it's negative. Notice it's squared. That forces this factor to be positive. It also forces this factor to be positive. Again, the square here does that. So the product slash quotient of all of them is positive. Now, what's the graphical interpretation of that? If y prime is positive, then our function must be increasing. Again, think about the slope of the tangent line. Positive slopes are increasing slopes. Okay, so we can indicate that perhaps with a little line like that. In this interval between 0 and 1, perhaps a half, It's the same story, isn't it? 16 times a half, that's positive. The denominators here are positive because of the square. I should say the denominator is positive because of the two squares. Okay, everything's positive. So again, y prime is positive. This suggests our function is increasing. To the left of 0, though, we have a different story. At negative 1/2, for example. Notice the numerator is now going to be negative 8. That's a negative value. The top is still forced to be positive because of all these squares. So we have a negative over a positive, which is negative. And graphically, that means our function must be decreasing. And likewise, if we're left of negative 1, we still have the same problem. The numerator is negative, and we have squares on the bottom keeping them positive. So overall it's negative, and overall our function is decreasing left to right. Now, before we move our attention to the second derivative, let's go back and look at this. We actually pick up one additional piece of information from knowing these slopes, from knowing the behavior of the first derivative. Notice here around 0 we're decreasing, and then we're increasing. And 0 itself, or at 0 itself, our function was continuous. So this has no alternative than to be a minimum, a local minimum anyways. Okay, so we might want to indicate that here as well. Okay, so now let's turn our attention to the second derivative. Again, doing a sign analysis, if we're to the right of 1, it looks like this factor has to be positive. Notice we have a cube here, so we do have to be careful about the sign of x minus 1. But this is positive, this is positive, this is always positive, this is always negative. Okay, so overall it looks like this is going to be a negative. Okay, graphically what does that mean? Well, our function must be concave down. So we can indicate that with a little arc like this. If it helps, you may want to consider combining the fact that it's concave down here with the fact that it is also increasing, which means you can only have a function that's behaving kind of like the left side of this upside down u and not the right, So you're increasing here and you're decreasing here. So you might want to replace this with maybe a half u, a half upside down u. So you're concave down and increasing. On the other side of 1 and between negative 1 and 1, what's going on? Well, now this guy has turned negative. This is still positive, however. This is still positive always, and this is still negative always. So it looks like net we are back to positive. And that's concave up. That's the graphical interpretation there. And notice it's good to draw a full U here because, again, looking up where it's decreasing and then increasing, it looks like the bottom of that U is going to be right at 0. We have a decreasing segment and an increasing segment. And then finally, to the left of negative 1, plug in negative a billion or something like that. This, of course, is always negative. This, of course, is still always positive. Don't forget the square there. Negative a billion plus 1, well, that's still very big. Negative cubed is still negative. And negative a billion minus 1, well, that's still negative. Cubed is also still negative. So we have 3 negatives here, 1 positive. It looks like overall this has to be negative. And so again, concave down. Okay, but keeping in mind what's happening above, we know it's decreasing. We might want to change that upside down U to just the half of the upside down U there that is decreasing. That'll help us with the graphing just a little bit. Okay, so now we've fleshed out all of the information we need here, but there's a couple more things we want to consider. First off, we've identified a few very special x values, negative 3, 3, 0, okay? These correspond to points on our graph. These are x values, they have y values. It'd be nice to know what those y values are so we could plot things more accurately. So to that end, let's make a little t-chart and put those x values in there and find their corresponding y values. Of course, negative 3 and 3 are easy because they were x-intercepts, so they have to be at height 0. Plugging in 0 is also pretty easy. Go back to the original equation here. 0 minus 9 is negative 9. 0 minus 1 is negative 1. Negative 9 over negative 1 is positive 9. Okay, so now I have 3 points that I can plot. So I know the behavior of the function at those 3 values. Now there's another place where we can fairly quickly determine the behavior of our function, and that is at the far ends of its domain. What is happening when x is moving way to the right or when it's moving way to the left? What happens as it approaches infinity, and what happens when it approaches negative infinity? Of course, we're talking about the limits at infinity here. To start with the behavior on the far right first, as x is getting closer and closer to positive infinity, if that makes sense, we want to find this limit. Okay. Of course, if this limit exists, we'll have a horizontal asymptote in our graph. Now, this being a rational function that we started with, there's a really, really short method for determining the value of the limit. Let's work this one out longhand, rigorously justifying things as we go, and then we'll mention what the shortcut is, of course. Notice as we consider x approaching bigger and bigger values, both the bottom and the top are getting very, very large because of this x squared term. What I could do is I could factor that x squared term out. It would be x squared times 1 minus 9 over x squared times 1 minus 1 over x squared. And then these things can cancel off. Effectively, I've multiplied top and bottom by 1 over x squared. Okay, and now it's very easy to see what happens to what's left. 9 over x squared, when x gets big, well, that goes away. That goes to 0. And 1 over x squared similarly goes away. And all we're left with is 1 over 1, or 1. Okay? Now, I said there was a shortcut. If you're looking at a rational function, just rational functions, you have a polynomial over a polynomial. Okay? Then if the degree of these two guys agree, the value of the limit can be obtained rather quickly by looking at the ratio of the leading coefficients. Of course, both of those here are 1. So we just have 1 over 1 or 1. Okay? Now, does it make a lick of difference whether x was approaching positive infinity or negative infinity in terms of evaluating this limit? No, not at all. This guy and this guy will still go to 0. We'll still cancel those x squareds off. We're still going to get 1. So let's consolidate this a little bit and just write that. Okay? We now have everything we need to get a really good graph of this function. Before we do that, though, let me make one final note. When we were picking our x and our x values to find y values for, there is one other one that we should add to our list if it's not already there. And for us, it was already there. But that extra one is the y-intercept. Okay? It's always really easy to find y when x is 0. So plug that in, and it's where it crosses the y-axis, so that makes it interesting. Notice we had already picked up x equals 0 here because it was an interesting point as far as our derivative is concerned. But if we had not put 0 here, we would want to consider that as well. Okay? Now, let's lay out our graph. Okay, we start by drawing our axes, and then finding all of these points and labeling those, like so. Okay, don't forget, looking at this first line, we also have a vertical asymptote at -1 and a vertical asymptote at 1. So let's label those, like so. This information here, of course, tells us that we have a horizontal asymptote at a height of 1. Okay, so let's go ahead and put that in on our graph, like so. 1 for the right and 1 for the left. You'll notice I left out this middle section here. I didn't dot the line all the way across. I do this purposefully. The horizontal asymptote only tells me what's happening when x is getting very, very big or when x is getting very, very negative. Very, very big, of course, is well to the right of 3. Very, very negative is well to the left of -3. It tells me nothing about what's going on in the middle here. a lot of time folks get kind of hesitant to cross a dotted line because they know they frequently can't cross these vertical dotted lines, certainly not with rational functions. So they extend that to horizontal dotted lines, and of course that can cause problems. You are free to cross this height of 1 here in the middle of your graph. Okay, this only tells you what happens way out here and way out here. So I just put the dotted lines there and there. Okay, now let's take this one subinterval at a time. Starting here well back towards negative infinity, we need to be very close to this dotted line. We need to end up here at this -3 as our first x value of interest. We need to be right on the x-axis. We need to decrease to it in a concave down way. All right, there's not too many ways you can draw that. Something like that. Okay, from -3 to -1, now we go below the x-axis. We continue to decrease. Okay, we're approaching a vertical asymptote, so we're just going to keep on going down in a concave down way to negative infinity. Okay, something like that. When I jump across and return on the other side of -1, notice now I need to be above the x-axis, so that means I need to reappear here. Okay, I need to be headed down, decreasing. I need to be decreasing in a concave up way, leveling off with a horizontal tangent at 0 to create a local min. Okay, so I level off right there. That's x equals 0, height of 9. Create a minimum. Now I go back up. I'm increasing. I continue to do so in a concave up way. I continue to stay above the x-axis, flying off on the next vertical asymptote. So it looks like we have something like this. And then when I jump on the other side of this asymptote, notice now I'm again below the x-axis, so I must have been down here. Okay, I should be on the rise in a concave down way, headed towards this x-intercept at 3. Something like that. And then as I pass 3, I now am above the x-axis. I continue to increase in a concave down way to end up over here at this horizontal asymptote, or very close to it, getting closer all the time. Okay? And that is our graph. Notice this graph has a certain symmetry about the y-axis. Okay? We could have deduced that way back here when we looked at our original function. It doesn't matter whether I plug in 3 or -3. Because of those squares, I'm going to get the same thing. Whether I plug in x or -x, I get the same thing. This is an even function. It has a symmetry about the y-axis. Okay? Which really means we could have shortened our work substantially here just by considering what happens on one side and then duplicating with a symmetric image on the other. We could have just looked at what happens to the right of 0 even here and here and here, okay, in our analysis. But it's nice to see the kind of double check there that one side has on the other. Okay, so this is the graph of that function. We should label some stuff in here. This has a horizontal tangent. Okay, it is also a local minimum, like so. We have x-intercepts here and here. Going back to this point, this is also a y-intercept. Okay, and that captures pretty much everything. Okay, so let's put a box around it and call it done. And that's it.